Alright, so this is probably gonna be an extremely boring stream. Where's my phone? Oh, there it is. Yeah, so today is probably gonna be an extremely boring stream. So I always wanted to probably learn WebGL, but I got lazy and didn't feel like doing it. Really lazy, like extremely lazy. Like I didn't want to do it because it's just so much math. So I decided maybe I should just stream it. Just stream me learning this, however boring it's gonna be. Yeah, so I am on webglfundamentals.org and I'm trying to learn it so I can do some graphics. I think that'll be pretty cool. And there's a lot going on here. And there's concepts that I do not understand, so we're definitely gonna try to figure it out. Yeah. Yeah, so I'm just gonna get started. So it says WebGL fundamentals, WebGL from the ground up, no magic. There are a set of articles that'll teach WebGL for basic principles. They are not old rehash of out-of-date OpenGL articles like many others on the net. They are extremely new, discarding the old, out-of-date ideas and bringing you to full understanding of WebGL really is how it really works. Alright, let's go. So long, so boring. Okay. Alright, it says WebGL is often thought of as a 3D API. People think, I'll use WebGL and magic, I'll get cool 3D. In reality, WebGL is just a rasterization engine. A rasterization engine. And I looked up rasterization because I was like, what the heck is that? But yeah, the process in which modern display systems turn electronic data or signals into projected images. Basically, it tells you how to display pixels on a screen. That's what I got from that. Yeah, so it's a rasterization engine. So basically, how to display pixels on a screen or monitor. So that's what they're saying here. And it says it draws points, which, okay, I know what a point is. Lines, triangles, that's great. Based on the code you supply. Makes sense. Yeah, so this is the reason why I want to learn WebGL, because I want to make games. And I think that'll be pretty cool. But there's a lot of math involved. A lot of concepts involved, so that's why I'm just looking over it. Yeah, so it says get into WebGL. To do anything else is up to you. Provide codes to use points, lines, and triangles. So it's a lot of geometry, a lot of matrices. I took this course in college, computer graphics, and it was very tough to understand. And it was terrible for me because I didn't take linear algebra, and that was a prereq to enter this class of computer graphics. So I was definitely struggling. But yeah. And it says WebGL runs on the GPU, so your graphic processing unit on your computer. So yeah, obviously. And as such, you need to provide the code that runs on the GPU. So that's fine. You provide that code in the form of pairs of functions. So those two functions are called vertex shaders and fragment shaders. So I'm actually going to take notes here so I know what to do. So just some notes, that just some vocab to learn. So rasterization is basically how to display pixels on a monitor. So that's one concept that we learned here. And then it also says that you provide that code in the form of pairs of functions. Those two functions are called vertex shaders and a fragment shader, and they are each written in the very strictly typed C and C++. Ugh, Like C and C++ is really hard concept for me because they're little lower programming languages. So there's high level programming language, which are very abstract and it's easier to get into. But C and C++ are like a little low. You have more control on like how data is stored and how to retrieve it. So it's a little harder to understand. And I struggle a little bit more with C and C++. But yeah. So it says the two pair of functions, so the vertex shader and the fragment shader, which I have no idea what are those, written in C, and they're in a C++ like language called GLSL. So we'll come back to that. I don't know what that exactly means. And when paired together, they are called programs. It says a vertex shader's job is to compute vertex positions. So that's not helpful definition, but we'll write it down for future reference. Okay, so a vertex shader's job is to compute vertex positions. Based on the positions, the function's outputs, WebGL can then rasterize various kinds of primitives, including points, lines, or triangles. When rasterizing these primitives, it's called a second user supplied function called a fragment shader. Okay, that was a mouthful. Okay, let me see if I got that right. So a vertex shader's job is to compute a vertex position. Let's define vertex really quick because I'm not entirely sure. So angular point of a polygon. So a vertex we can define as an x, y, I'm guessing. Or maybe like a point. Yeah, a point where two or more line segments meet. So that's how we'll define a vertex. All right, so we'll just say a vertex is a point, just to be simple with it. And then a vertex shader's job is to compute the vertex positions. So basically, tells it where it needs to go. So we'll simplify that. So the vertex shader basically defines the location of the vertex. That's how I'm gonna say it. And then based on the position, the function outputs WebGL can rasterize various kinds of primitives, including points, lines, and triangles. Cool. When rasterizing these primitives, it's called a second user supplied function called a fragment shader. Okay, so a fragment shader job is to compute a color for each pixel of a primitive currently being drawn. So I understood that one more than I did the vertex shader. So a fragment shader is rasterizing each pixel. So basically it defines the color. And this gnat. Okay, so far there's the vertex shader, which defines the location of each point, and then the fragment shader comes behind and colors the pixels in. So far, I think I'm understanding it slightly. Alright, so nearly all of the entire WebGL API is about setting up state for these pairs of functions to run. Okay, so like they said, you provide the code in the form of pair of functions. So that's the vertex shader and the fragment shader are the pair of functions. And then those are each written in GLSL, which then pair together their program. Gotcha. And then nearly all of the entire WebGL API is about setting up the state for these pairs of functions. So the program, the vertex shader, and the fragment shader. So nearly all of the entire WebGL API is about setting up state for these functions. So that's the main thing to get into. So we always are, so nearly all the time we'll be using the vertex and the fragment shaders. So that's good to know. For each you want to draw, you set up a bunch of state and then execute a pair of functions by calling draw arrays and draw elements, which executes your shaders on the GPU. Okay, any data you want those functions to have access to must be provided to the GPU. Makes sense. There are four ways a shader can receive data. There's attributes and buffers. So buffers are an array of binary data that you upload to the GPU. Actually, I want to just copy that exact line verbatim and put that in the notes. Okay, so just to recap, we have the vertex shader, we have the fragment shader. So the vertex shader defines positions of points. Fragment shader defines the color of the pixels. And nearly all the functions, everything in the WebGL API use those two functions to rasterize images. Makes sense. And then anything that we want to provide to the GPU needs to go through these four methods. So attributes and buffers, uniforms, textures, and variants. Fun. So, it's a lot to take in. Okay. So buffers are arrays of binary data that you can upload to the GPU. Usually buffers contain things like positions, normals, I have no clue, texture coordinates, vertex colors, okay, etc. Although you're free to put anything you want in them. That's great. Attributes are used to specify how to pull data out of your buffer. Okay, so we have buffers that just contain any binary data. Attributes define how to pull data from the buffers and provide them to your vertex shader. Okay. Just copy that verbatim, paste that right there into notes. Okay, let's see an example. So for example, you might put positions in a buffer as 3 32-bit floats per position. What? So you might put positions in a buffer as 3 32-bit floats per position. Don't understand that, but we'll come back to it. You would tell a particular attribute which buffer to pull the positions out of, what type of data it should pull out, and 3-component 32-bit float numbers. What offset in the buffer the position starts, and how many bytes to get from the position to the next. That made sense to me. Basically, you define how to pull the data out. That's what the attribute is saying. And the way to define that, you say, oh, it's a 32-bit float with the offset of X bytes. That made sense to me. And it says buffers are not random access. Instead, a vertex shader is executed a specified number of times. Each time it's executed, the next value from each specified buffer is pulled out and assigned to an attribute. That kind of made sense to me. So buffers are not random access. Instead, a vertex shader is executed and specified a number of times. Each time it's executed, the next value from each specified buffer is pulled out and assigned to an attribute. So it's execute. So if you execute the vertex shader 9 times, and you say pull 32 bits in, then it's gonna get the first 32 bits, and then it's gonna get the next 32 bits and assign it to attribute. Then it's gonna get the next 32 bits and assign it to attribute, so on and so forth until you've done it 9 times. So that makes sense to me. Okay. Let's keep going. Uniforms. Uniforms are effectively global variables you set before you execute your shader program. So we will not be using uniforms because global state is the devil. So never use global state. Always pass it in. So if we're passing in, so we're always going to pass in, or we're always going to use a buffer and then use attributes to get the data out the buffer. We're never, probably never, ever going to use uniforms because we don't like global variables. All right, maybe some use case there, but most likely never. Okay. Textures. Textures are arrays of data you can randomly access in your shader program. The most common thing to put in a shader is image data, but textures are just data and can just as easily contain something other than color. Okay. Seems less likely, less common in this early stage, so we're just gonna not worry about textures. And then variants. Variants are a way for a vertex shader to pass data to a fragment shader. So we actually might be using this quite often, variants. So a way for vertex shaders to pass data to the fragment shaders. Depending on what is being rendered, points, lines, or triangles, the value set on a variant by a vertex shader will be interpolated while executing the fragment shader. So not entirely sure what that all means, but I need an example to actually test out some of this stuff. Alright, so that was a lot. That was a lot at the very beginning. My head is already spinning. Snack. Okay, so finally an example. So it says WebGL hello world. So WebGL only cares about two things: the clip space coordinates and colors. So I'm guessing, so just from everything that I read, clip space coordinates and colors. So that's what the two things that WebGL only cares about. So I'm guessing the clip space coordinates has to do with the vertex shader, and the colors has to do with the fragment shaders. Just from everything that I read so far. Now it says your job as a programmer using WebGL is to provide WebGL with those two things. You provide your two shaders to do this. Oh, see, like I said. Oh, see, I was already ahead of the curve. So it says a vertex shader which provides the clip space coordinates, which I just said, and a fragment shader that provides the color. See, it just made sense. It clicked the minute I read those two words, clip space coordinates and colors. So that made perfect sense because vertex has to do with points. So a point has an X and a Y, so it has a position. So that made sense when it brought up clip space coordinates. And then fragment shader had to do with rasterization. So actually displaying the pixel on the screen using color. So that made perfect sense when they said all it cares about is clip space coordinates and colors. Alright, so the clip space coordinates always goes from -1. Okay, so when I was taking my computer graphics class, this was what confused me the most. Because this made no sense to me whatsoever. Okay, so the clip space coordinates always go from -1 to +1, no matter what size your canvas is. So it doesn't matter the dimensions of your canvas. So your dimensions could be 32 pixels by, or 32 inches by 32 inches. It can be 64 inches by 64 inches. It could be 1080 pixels by what's the resolution for 1080? It can be 1080 pixels by 1920. It doesn't matter. Doesn't matter the size. It's always going to be from -1 to +1. From horizontally and vertically. So horizontally, -1 is on the left, +1 is on the right, and then vertically, -1 is on the bottom, +1 on the top. That's the clip space. All right, so here is an example. Here's a simple example that shows WebGL in its simplest form. Let's start with a vertex shader. Okay. Oh gosh. Ooh, my brain. Okay. Brain already hurting. Okay. An attribute will receive data from the buffer. So I remember that. So here it says any data that we want any data you want those functions to have access to must be provided to the GPU. And it says attributes are used to specify how to pull out data from the buffer. So in WebGL, it looks like we define an attribute by saying attribute. We say the type, I'm guessing, vec4, and then we say the variable name. This is just a guess. It's just me from programming so many times. So attribute, vec4, and then variable name. So all shaders have a main function. Cool. And then GL position is a special variable for a vertex shader and is responsible for setting. Okay, makes kind of sense. Kinda. So this is our shader main. GL position is a special variable for vertex shaders, and then we're assigning it an attribute. So the attribute is pulling from our buffer, I believe. Ooh, okay. When executed, if the entire thing was written in JavaScript instead of GLSL, you could imagine it would be used like this. Yes. Okay, so I kind of understand what vec4 is. So I believe it means that it has, this is the kind of like coordinates. So this is X, Y, Z, and I think maybe W is the fourth dimension one. X, Y, Z, is it W, I think? I think that's the fourth one, is W. So that's why I think it's called vec4. So I think that's it. So they're saying if it was written in pure JavaScript instead of JLSL, which we'll have to look up later because I don't know what that is still. It will look like this. So this would be X, Y, Z, W, and then X, Y, Z, W, X, Y, Z, W. So it's saying that its position would be 0. So on this chart, it would probably be right here in the dead center. And then it would be 0, 0.5. So it'll go from, so the first point would be in the center. The second point would be 0, 0.5. So it'll be here, right here, like halfway between +1 and 0. So it'll be right here. That's the second point. And then they're saying the third point would be somewhere here. So 7/10 the way to the right. So when it connects, it'll do a triangle. So it'll be a right triangle from here, here, here. Is my guess, at least. Being a programmer for 5 years, that's my guess. I'm pretty sure that's right. So, but yeah, so this is pseudocode for if it was in complete JavaScript. And they're saying draw arrays. So stride is 4, which I don't know what that is. Size is 4. And it would loop through I0. Yep. there's the offset. Offset, where's that at? Offset. Oh, offset's here. Call it drawaway. Offset, yep. Yep. Plus stride, sure. Attributes. A position. Buffer position. Slice. The start plus the start plus the size. I don't know where size is defined for. Then run vertex shader. Do something with GL position. So that kind of makes sense to me. So basically what they're saying is it would basically do the start. The start would be if the offset, so if this ran, so it's saying that it run, well, I don't know how many times it runs, but the offset will likely be 4, I want to say. But if the offset is 0, if it starts off and then on this initial run, the offset would be 0, the I would be 0. Well, yeah, offset 0, I would be 0, stride would be 0. So start would be 0 here, and then start would be 0 and size would be 4. So it would slice from 0 to 4. So it would grab these it would grab the first 4. Because that's basically what the attribute's doing. The attribute, I think, oh, that actually made perfect sense to me now. Now that I see a JavaScript example of it, now it's making sense. This is saying it's a vec4. So if the buffer is like, if this is the buffer and it's saying vec4, then it's saying grab the first 4 of the buffer. So that's why it's saying vec4. So now it's starting to make sense now, just from this JavaScript example. So it's saying grab the first 4 from a buffer and then store it in a position. And then on the next run, it's gonna move the offset. So it's gonna grab the next 4. So the offset's gonna be the offset's gonna be in the next 4, and it's just gonna grab this. So now I understand what vec4 is now. Kinda, sorta. All right, so let's keep moving along. In reality, it's not quite that simple because position buffer would need to be converted to binary data. And so the actual computation for getting data out of the buffer will be a little different, but hopefully this gives you an idea of how vertex shaders will be executed, which that definitely helped. I mean, I would like to have seen an example of draw arrays, but that definitely helped a little bit. And then it says next we need a fragment shader. So fragment shaders don't have a default precision, so we need to pick one. That made no sense to me. That really didn't make any sense to me. So fragment shaders don't have a default precision. I don't know what that is, so we need to pick one. Medium is a good default. It means medium precision. So medium precision. Okay. So it's one of those special types. So attributes is a special type, and I'm guessing precision is a special type. So I don't know what precisions are, but that seems to be the style in GLSL, is that you do the special name like attribute precision, and then you do the type of that. So attribute of vec4. So I'm guessing there was also a vec3, which defines how to take data out of the buffer. And then here seems to be a precision, because shaders don't have default precision, whatever that means. And this is a medium precision, and we're defining it as a float. Okay. And then of course every shader has a void main. Okay, so and then we use the GL frag color. It's a special variable for fragment shaders, just like GL position is a special variable for vertex shaders. And it's responsible for setting. So yeah. I don't know how this gives you a reddish purple, but it does somehow. I'm sure there's like a list of that'll help you out right there. But 100.51. Okay, my brain. So above they're setting the GL frag color, which is okay. Maybe this makes sense because RGBA, maybe RGBA. I think that's what it might be. So RGB or yeah, RGBA. So red, green, blue. And then A would be alpha, which I'm thinking it might. Oh, look. Oh, see, I've done programming so many times that I know exactly what they stand for. So it says which is 1 is red, which is the first position. 0 is for green. Yep. And then blue is for it's the third position, and then 1 is for alpha. So the reason why I know RGBA is because I've seen it in like CSS. So now it's all clicking. And it makes sense because that's how I vaguely know how monitors work. Vaguely, just very vaguely, but I think I think the pixels, like the monitors have lights that you can control what color displays based on these 3 values. I think maybe it's been a minute since I've seen it. Like I understand. It has been a minute. But for the most part, I vaguely recall that by changing these values for individual pixels, it'll give you certain colors. So that's where I think it's coming from. I'm gonna have to do some further research on that, but that helps. Okay, so okay. I might can like start coding in a second. It says colors in WebGL go from 0 to 1, so that's perfect for me. Now that we have written the 2 shader functions, let's get started with WebGL. First, we need an HTML canvas element. So they have a canvas, and then JavaScript, we can look that up. So in JavaScript, you can obviously select the element on the page by using query selector. So they use query selector, they use the hash C. So that's how you get an ID in JavaScript. And now they can create the WebGL rendering context. So you do get context, WebGL, you specify that as WebGL, and then yeah. All right, so brain. Okay. Now we need to compile those shaders to put them on the GPU. So first we need to get them into strings. Okay. You can create your GLSL strings any way you normally create strings in JavaScript. By concatenating by using Ajax to download them, by using multiple line template strings, or in this case by putting them in non-JavaScript. Okay, that kind of made sense to me. Kinda. You can create your GL strings any way that you normally create strings in JavaScript by concatenating them by using Ajax to download them, by using multiple line template strings. I'm gonna have to come back to that one because I might understand this, but this sounds like the simpler solution. So, or in this case, by putting them in a non-JavaScript type string tag, which makes sense. So this is the GLSL. So this is the attribute. So this is our vertex shader because it's using GL position. And this is our attribute, which pulls the data from the buffer. And then here is our fragment shader. It has it listed here. So fragment shaders, which doesn't, so fragments don't have default precision. So they define a medium precision and then specify a reddish purple color. So the only thing I see that's missing is probably the buffer. So I'm sure they're going to explain it next. So in fact, most 3D engines generate GLS shaders on the fly using various types of templates, concatenation, etc. For the samples on this site though, none of them are complex enough to need to generate GSL at runtime. Next, we need a function that will create a shader, upload the GSL source, and compile the shaders. Note, I haven't written any comments because it should be clear from the names of the function what is happening. Okay, wow, that was a lot. So they need a function to create the shader, upload the GL source, and then compile the shaders. Kind of makes sense. So to create the shader, you pass in the GL, which I don't see anywhere. Then the type, the source. So it says GL create shader type. I don't understand any of this. Shader source, shader source. I don't know what that is. Compile shader, passing in the shader, and then success, get shader parameters. Made no sense whatsoever, but we'll come back to it. We can now call the function to create the two shaders. Okay, maybe now it's making a little bit more sense. So now it's grabbing those script tags. So it's grabbing these two script tags here as elements. It's passing in the GL object. It's specifying the type, which is a vertex shader, in the fragment shader. And then that's the source. Okay, now it's slowly making sense. So in order to create the shaders, we just need a string, which I believe this is it, because it said that we could use any type of multi-line template strings, or we can use non-JavaScript type script tags. In this case, we're using the script tags. So in that case, when they call create shader, it's passing in the global GL object. It's specifying that it's a vertex shader or a fragment shader, which is type. So when you create a shader, you say GL, which is the global GL object. You say create shader on it, and then you pass in the type, which this is like it's probably like some integer or something, which is vertex shader or fragment shader. It creates the shader based on the type that you pass in, and then it does the shader source, which is this right here, which is this script tag. So it's passing that in. Yeah, so you create the shader first, you pass in the source, and then you compile it. So that's the shader, that's the source, and then you compile it. And then on success, so GL shader parameters, shader compile status, you check the success and then you return the shader. Then it looks like after everything is done, you delete the shader. Man, that's some complex stuff right there. Now it says we can now call the functions and create the two shaders. That's what it does. Then we need to link the two shaders into the program. Makes sense because what it said earlier is that those two shaders work together to make a program. So now they create a function called create program, which takes in a GL object, the vertex shader and the fragment shader. So then they call GL create programs on the global object. They attach the vertex shader to the program. They attach the fragment shader to the program. And then they call link program. And then on success, they return the program. And then delete the program after everything's done. And then you simply call it create program, which is, that's what it's running. All right, brain is fried now. Okay, so now that we created a GLSL program on the GPU, we need to supply data to it. The majority of WebGL API is about setting up states to supply data to our GLSL programs. In this case, our only input to our GLSL program is a position, which is our attribute. The first thing we should do is look up the location of the attribute for the program we just created. What? Let me read that. Okay, Web API is about setting up states to supply the data to our GLSL program. In this case, our only input to our GLSL program is a position. Yo! What's up? Natsack. That's funny. But yeah, so in this case, our only input to our GLS program, which is an attribute, the first thing we should do is look up the location of the attribute for the program we just created. So it looks it up. That kind of makes sense to me. You create the program, then you look up the attribute. Looking up the attribute location is something you should do during initialization, not in the render loop. Attributes get the data from the buffer, so we need to create a buffer. Yeah, creates buffer, makes sense. WebGL lets us manipulate many WebGL resources on a global bind points. You can think of bind points as internal global variables inside WebGL. First, you bind a resource to a bind point, then all other functions refer to the resource through the bind point. So let's bind the position buffer. I don't quite understand that one. I get that they create a buffer, so WebGL lets us manipulate many WebGL resources on global bind points. You can think of bind points as internal global variables inside WebGL. First, you bind a resource to a bind point. So obviously our array buffer is a resource. Then all other functions refer to the resource through the bind point. Okay, so let me actually copy that and put it into my notes because that's a good one. So we created a buffer called position buffer, and then we did a bind buffer, GL bind buffer, GL array buffer, position buffer. Now we can put data in that buffer by referencing it through the bind point. Did that make sense to me? Not quite. So this looks like a function on the GL global object that this is the bind point, and then we convert our array into float 32, whatever that is, and then GL static draw. It says there's a lot going on here. The first thing is that we have positions, which is in a JavaScript array, which is great, cool. WebGL, on the other hand, needs strongly typed data, so the part, that makes sense. WebGL, on the other hand, needs strongly typed data, so the part new float 32 array creates a new array of 32-bit floating point numbers and copies the values from position. That actually makes sense now. So WebGL takes strongly typed data type data, so we convert these into 32-bit floating. That makes sense. GL buffer data then copies that data into position buffer, which kind of makes sense, maybe. Like it copies it into position buffer, but it's called array buffer. On the GPU is used the position buffer because we bound it to the array buffer bind point above. Okay. It creates a new array of 32-bit floating point numbers and copies the values from positions. GL buffer then copies that data into position buffer on the GPU is using the position buffer because we bound it to the array buffer bind point above. Okay, now I might understand it a little bit more. So we created a position buffer. We created a buffer called position buffer, and we bound it to array buffer, the bind point, and then we pass the data of our float 32 positions into, since array buffer is bound to our position buffer. That makes sense. Okay, how do you access this into... It's using the position buffer because we bound it to array buffer point above. The last argument, static draw, is a hint to WebGL about how we'll use the data. WebGL can try to use that hint to optimize certain things. It tells WebGL we are not likely to change the data much. The code up to this point is initialization code that gets run once when we load the page. The code below is the point. The code up to this point is initialization code that gets run once when we load the page. The code below this point is rendering code, or code that should be executed each time we want to render or draw. Oh man, this is so long. Okay, we're almost there. We're almost to some actual code or work. But I pretty much get the gist of it. Okay, so rendering. Before we draw, we should resize the canvas to match its display size. Canvases just like images have two sizes. The number of pixels actually in them, and separately the size they are displayed. Before we draw, we should resize the canvas to match its display size. Canvases, just like images, have two sizes. The number of pixels actually in them, and separately the size that they are displayed. Okay. I'm gonna have to come back to that. I didn't quite understand that. CSS determines the size the canvas is displayed. You should always set the size you want a canvas to be with CSS, since it's far more flexible than the other method. To make the number of pixels in the canvas match the size that's displayed, I'm using a helper function you can read about here. We'll come back to that. In nearly all of those samples, the canvas size is 400 by 300 pixels if the sample is run in its own window but stretches to fill the available space if it's inside an iframe like it is on this page. By letting CSS determine the size and then adjusting to match, we easily handle both these cases. WebGL utilities resize the display size. We'll come back to that. That sounds like some other problem. Yo, Dark Chris, what's up? What's up? We need to tell WebGL how to convert the clip space values. I'm so confused. Oh man, I am so confused too. Like, this is like so complicated. Like, there's so much math involved just to do like 3D and 2D rendering. So it says we need to tell WebGL how to convert from the clip space values we'll be setting back into pixels, often called screen space. What? Oh gosh. Ugh. We need to tell WebGL how to convert from clip space values we'll be setting on GL position back into pixels, often called screen space. To do this, we call viewport and pass it the current size of the canvas. Okay, kinda understand this one. So GL viewport, it says 0, 0, which I think that's the starting position, I believe, and then the width of the canvas and the height of the canvas. This tells WebGL that the -1 plus 1 clip space maps to 0. That kind of makes sense to me. So it says the clip space from -1 to +1 maps to 0 to the width of the canvas, and for X, and then for 0 to the height of the canvas for Y. So we clear the canvas. We use 0, 0, 0, 0, 0 for respectively. So for this case, we're making the canvas transparent. So they cleared the color. I don't know what that one is. We tell WebGL what shader program to execute. Tell it to use our program. Yep. Next, we need to tell WebGL how to make the data from the buffer we set up above and supply it to the attribute in the shader. What? I get converting the clip space to screen space. Kind of get that. And then we clear it out. I don't know why we're clearing it out, but okay. I get that we tell it what program to use. Next, I barely understand all the word. Yes, see, exactly. It's the terminology. The terminology is very trippy. Yeah, just knowing the terminology is really difficult. Like, I've used this before, but that was like 7 years ago. Like, I haven't touched WebGL in 7 years, so I barely scraped by in my web computer graphics class, and I was just winging it, honestly. I had like partners who knew a little bit more than me, so they pretty much just did everything. So terminology is definitely hard. But yeah, I'm like a couple of paragraphs from actually trying it out myself. So we'll see how much I retained. I think I retained nothing, but we'll see. So you tell it what program to use. Next, we need to tell WebGL how to take data from the buffer we set up above and supply it to the attribute in the shader. So I kind of remember this before. So what was this again? I wouldn't know how to colleges though. I mean, my computer graphics class was hard because I didn't know the math. I mean, it was literally math. It was it was tough math. It was extremely tough math. Like linear algebra, I hated I hate geometry, so like linear algebra was really tough for me. So I vaguely remember what this was. I remember that we set up our attribute. Let me see. So yeah. It says looking at attribute positions is something that you should do during initialization that you're not rendering loop. Attributes get their data from the buffer, so we need to create a buffer. We need to look up the location of our attribute for the program we just created. I don't know why we need to look up the attribute's location. But it's a uniform. And that goes back to way up here, like it said that uniforms, any data that you want those functions to have access to must be provided to the GPU. And then uniforms are one of them. So you create a uniform by getting the attribute location. And then next we need to tell WebGL how to take the data from the buffer we just set up and supply it to how to take the data from the buffer we set up above. The Nightbot gotcha. I gotta take caps off. The Nightbot got the caps. How did I tell Nightbot to chill? This always happens. I know, I'm sorry. How did I tell Nightbot to chill? Chill, bro. I'm gonna have to figure that out later. I'm gonna have to tell Nightbot to chill. Oh, you trying to say what was an attribute? An attribute is the way to get things out the buffer. So for WebGL, you supply it data through a buffer. So a buffer is just, data for the vertexes. So like if you want to draw a triangle, you need the 3 points of a triangle. So you pass it as a buffer, and then the attribute tells it how to get it out of the buffer. So here's an example right here of a triangle. So it's saying that the first point on the triangle is 0, 0. So if you think of a graph, the first point is 0, 0. The second point is 0, 0.5, and then the third point is 0.70. So when you graph that and you add up the lines, it makes a right triangle. And so an attribute tells it how to grab the data from the buffer. So an attribute would say, okay, grab the first two here because that's the first point. and then next grab the next 2 points. That's the second point, and then the attribute would get the third point. So here's an example of an attribute. It's saying it's a vec4. So you can do things in 2D space, 3D space, and 4D space. So a vec4 saying grab it and is 4-dimensional. That's what 4 vec4 means. Well, technically, you can go all kinds of dimensions. It's not just 4 dimensions. You can go 5 dimensions. You can go 6 dimensions. You can go 7 dimensions. But usually, for the most part, we only go up to 4 dimensions. Because to solve problems in 3-dimensional space, you have to use the 4th dimension. Which is crazy. It blew my mind. But yeah, to solve 2D problems, you got to use 3 dimensions. And sometimes to solve 3-dimensional problems, you have to do 4th dimension. It said Nightbot timed me out for like an hour for replying to a question too fast. Nightbot is crazy. I'm gonna have to. Yeah, I'm gonna scold Nightbot. All right, so yeah, so we're almost about to get into some drawing of 3D graph or 2D graphics in a second. So I just need to finish reading this, and then I think I'll be ready to actually get to this example here of how it drew a triangle. Because it can get like pretty cool. Like once I get a feel for it, you can like. So this is an example of WebGL. See, like you see all those 3D cubes that's moving in the background. That's an example of what you could create. And you can create games and all kinds of things just from WebGL. But it's a lot of math. It's a lot of concepts. So that's what I'm trying to learn here. I think my programming is pretty good enough to kind of figure this out. So that's why I'm starting at the very beginning. It goes from fundamentals to image processing to 2D animation or 2D rendering to 3D, and then lighting. Lighting is the most confusing thing I have ever tried to figure out. Like it is incredibly hard, like to wrap your brain around. Super difficult. There's more than 3D and 2D. Yeah. Yeah, there's 4D, there's 5D, there's 60, there's 70. It just goes on and on and on. But since people can only see in 3 dimensions, that's why we go no higher than 4 dimensions. Because we just need to solve, because a lot of times to solve 3-dimensional problems, we need the 4th dimension. So since we only can see in three dimensions, we only have to go up to the 4th dimension. Isn't math great? Yeah, when you get into like matrix multiplications, solving problems, you got to go to the 4th dimension. All right, so back to this. Oh gosh. You're ruining my childhood. Ha, that's funny. All right, so back to what I was reading. We need to tell the WebGL how to take data from the buffer we set up above and supply it the attribute in the shader. That makes sense. Kinda. Okay, first off, we need to turn the attribute on. So you enable the vertex attribute array. Then we need to supply how to pull the data out. Okay, I remember that we bound the position buffer to the array buffer. That makes sense. We did that up here, so there's only two positions. So they're saying it's a size 2 components per iteration. It is a float because we got 32 bits. Normalize, don't normalize the data. Sounds good. Stride. 0 equals move forward. What? 0 equals move forward size times size of type each iteration to get the next position. What? And the offsets start at the beginning of the buffer. Okay, that made kind of sense. But yeah, so GL vertex attribute position. They pass in the attribute location, the size, so get the first two on the first iteration. The type, they're 32-bit floats, so it says float. Normalize is false, stride is 0. I don't know what this is really. Move forward size times size of type. I don't know what that is. And then offset is 0, so that makes sense. My Super Mario childhood. Oh, Super Paper Mario. I don't think I've ever played Paper Mario. I'm gonna let I get my watch time up. Thanks. Okay, so a hidden part of vertex attribute pointer is that it binds the current array buffer to the attribute. In other words, now this attribute is bound to position buffer. A hidden part of vertex attribute pointer is that it binds the current attribute buffer to the attribute. In other words, now this attribute is bound to position buffer. That means that we're free to bind something else to attribute buffer bind point. What? The hidden part is that it binds the current attribute, the array buffer, to the attribute. What? In other words, now the attribute is bound to position buffer. Oh, maybe it does make sense now. That means we're free to bind something else to array buffer bind point. The attribute will continue to use position buffer. Note that from the point of view of our GLSL vertex shader, the A position attribute is a vec4. Vec4 is a 4 float value, which I already knew that from just guessing. In JavaScript, you could think of something like A position. Yeah, that's what I pretty much guessed. X, Y, Z, W. Above, we set a size of equals 2. Attributes default to 0, 0, 0, 1. So this attribute will get its first two values, X and Y, from our buffer. The Z and the W will be default 0, 1, respectively. After all that, we can finally ask WebGL to execute our GSL program. I don't know what that is. Primitive type GSL, triangles, offset 0, count 3. Maybe that made sense to me. Because the count is 3, this will execute our vertex shader 3 times. That made sense. The first time, a position X and a position Y in our vertex shader attribute will be set to the first two values of the position buffer. So that makes sense too, because we said oh man, wow, this is a lot. Okay, so here's our vertex shader. We have our attribute set up in GLSL. We say, okay, this is some special variable that we set our position from, attribute our attribute gets values from our buffer. We told it get the first two values in our buffer. So this is our buffer. We said get our first two values because we specifically said the size is 2 here. So it gets our first two values and then it executes it 3 times. So but how does it go to the next one? That's my question. The second time will be the second two values, and the last time will be the last two values. Because we set primitive type to triangle, each time our vertex shader is run 3 times, it will draw a triangle based on the 3 values we set. No matter what size our canvas is though, values are in the clip space coordinates that go from -1 to 1 in each direction. Because our vertex shader is simply copying our position buffer values to GL positions, the triangle will be drawn at clip space coordinates. Converting from clip space to screen space, if the canvas size happened to be 400 by 300, we get something like this. So it'll convert the clip space to screen space. WebGL will now render that triangle for every pixel it is about to draw. WebGL will call our fragment shaders. Our fragment shaders will just set the GL frag color to 100.51. Since the canvas is an 8-bit per channel canvas, that means WebGL is going to write the values 255, 0, 127, 255 into the canvas. Here's a live version. All right, now I'm actually gonna attempt this crap. Wait, I thought I was assuming that they could do this in the very beginning, that they could just change this maybe. Oh man, that's a lot of reading. Okay, all right, let's try it out ourselves. I've been doing a lot of reading. I haven't done any coding, so let's actually try this out. Let's see how much I remember from reading all that. And draw our first 2D shape. And then hopefully eventually we can get to 3D. Okay. My green screen. Alright, so we're gonna open up in VS Code. Alright, let's see. Okay, so what I remember it saying is, so what we're gonna do is first create our, so for WebGL we need a vertex shader and we need a fragment shader. So vertex shader, and then we're gonna create a fragment shader. Okay, and then the next thing is that in order to take, so in order to get data from our buffer, we have to use attributes, textures, uniforms in order to do that. So we're going to create an attribute. Man, this tab 9 is smart. Yeah, so we create an attribute. We're going to do vec4, and then we're just going to simply call it a position. And then in order to create a shader, you have to use a main function. And then you call GL position. So that is a special variable. and then you simply pass in the position. If I remember correctly. And then for a fragment shader, you do the same thing. You do a main function, and you simply call GL frag color, I believe. And then you just pass in a color. So I don't know what color this is, but we'll just do that. Okay, I kind of understand now. Now I gotta go back. Alright, so I created my vertex shader. Oh yeah, I gotta do type. I think it can be anything. The type can be anything. Oh yeah, I forgot the precision because by default it doesn't have precision, so I gotta do that. So precision, medium, precision, float. Yep. And so then you have to create your shader and all that crap. So let me just double check. Is that right? Alright. Let's do another script tag. Alright, so you have to create your shader. So I remember last time it like took a global object, and then it took the type, and then it took the source. And I don't know exactly how it created the shaders, but yeah, so there's a GL function called create shader. So your const shader equals gl.create shader, and then you pass in the type, and then you bind. So let me do this. So do some comments. Yep, and then obviously you do. So you create a shader of the type, so either a vertex shader or a fragment shader. And then you bind the GLSL or GLSL code to the shader. So then we call it GL shader source. So shader source. And then you compile it. Then you basically compile the code. And then you basically check if it's a success. So get shader params if it's a success. We're just gonna assume that it's a success. Oh, maybe not. We probably want this error message actually. So GL get shader param, and then the GL compile status. If success, we want to return the shader. If not, we want to console log the error. The GL get shader info log. And then delete the shader. Log the error message. Alright, cool. So that's how you create the shader. So that's important. We create the shader, whether it's a vertex or a fragment, and then we bind the GLSL code to the shader, and then we compile it. Now we gotta import the WebGL library. I don't know where that's at. Let me see. Here we go. Yeah, I think that's it. Maybe. Is that it? Like, that has to be it. Because this is the vertex shader. This is the fragment shader. Like, this has to be the WebGL library. Because that's how we get our global object. Yep. And now, so that creates our shaders. Now I gotta create our buffer. Yeah, so basically, so to create our shaders, we gotta get our vertex shader. We do document.query selector. fragment shader. And then we want to create our fragment shader by calling create shader, passing in the GL, passing in the type. So I think it's GL dot vertex shader, maybe. Maybe that's it. Let's see. Yep, that's what it was. And then you pass in the source, so that's vertex shader element. And then you start it all over again. Call that create shader, fragment shader, yep, and then fragment shader element. Yep, yep, and that should do it. We also need a canvas. Just call it art. I like backticks, so let's just change all those. Yep, so we created all our shaders. Now we have to create a program. I forgot how to do that. Let's see. So we create a program. Yep. Vertex shader, fragment shader. And then I think you have to tell it to use the program. Yep. Yep, tell it to use the program. And then we need to get the location of our attribute. Well, let's create our buffer first. We'll say 0, 0. We'll say, we'll put 0, 0.5. And then we'll say -1, 0 for our positions. And then we'll create our buffer. So in order to create our buffer, I think you do gl.createBuffer maybe. And I think you have to bind it. Oh, I can't even remember. no, you create a buffer first. Just say buffer equals gl create buffer, and then you gotta bind I think the way it said it was bind point. Yeah, so bind points are internal global variables inside WebGL. So we bind to this global array buffer. And then we want to say what was it? Buffer. So we bind our buffer to the global array buffer, which is a bind point inside of WebGL. And then we put, now we need to put the data in there. So we say, so this creates our buffer. And then we have to bind our buffer to a global variable in WebGL. And then we have to put our data into the buffer. So we're putting our data into this global variable here. We have to change this one into a float 32 and then draw. Yep, that's exactly what we want. So here we pass data to the global variable. We convert to strongly typed array, and then we tell WebGL about the data. All right, that's a lot. So we create our buffer, we bind to the global variable in WebGL, and then we basically pass in the data into our global variable. Alrighty, so we're almost there. So now what I want to do is let's tell it how to take the data out. So first we need the location. We need the location of our attribute. So GL, how do you get the attribute location? Get attribute location. Pass in the program. The name of ours is position. called it position, so that's it. So we get our attribute location, we need to enable it. So where is that at? It says next we need to take the data from the buffer we set up above and supply it to attribute shader. In the shader, first off we need to turn the attribute on. Yeah. I don't know why you need to turn the attribute on, but okay. So below here, turn attribute on. So you say GL dot enable attribute, and then we pass in the attribute location. So we turn it on. And then we basically bind buffer. I already did that. I already bind the buffer. I already passed the data into the buffer. And then basically we're going to tell the attribute how to get the data out of the buffer. So what we do is we do gl dot vertex attribute pointer. Vertex attribute pointer, we pass in the attribute position, attribute location. We say that we want to grab 2. The type is gl.float. Normalize, we don't want to do that. Stride 0, offset 0. Yeah, so basically tell it how to get the data from the position buffer. Am I missing anything? Alright, so the last few things I think are the resizing. So I'm just going to copy and paste that. This is a to-do list to comment later. Then convert clip space to display space. And then basically clear out the canvas. What is going on here? not tabs. What is going on? Alright, had to convert the spaces to tabs. Okay. Alrighty, I think I understand. Now, in the final steps, we have to draw. And then lastly, after that, we say gl.draw. Draw arrays. We tell it gl.triangle. And then we say offset 0, count 3. So execute it 3 times. Per count, and then tell WebGL what program to use. Alright, now what I do with the canvas? I'm sure I do something with the canvas. Oh yeah, I forgot that part. Oh. Oh, that's what GL is. Oh. The GL is the context of the canvas. I didn't know that. Interesting. So canvas get context. WebGL. Now it's all making sense, honestly. So I got the canvas, and then the GL is the context of the canvas. And then I simply create the shader by passing the context of the canvas. Tell it is a vertex shader, it's a fragment shader. Create the program, give the attributes location so I can later tell it how to get the data, create the buffer, bind it to the global variable, pass in the data to the buffer, enable the attribute. Convert from clip space to screen space. Use the program draw. Alright, let's see what happens. I doubt I got it right on my first try. Cannot read property of null. Supposed to be a hash. GL get attribute location is not a function. Lies and deceit. Oh, get attrib location. Buffer bind buffer is not a function. Come on. Oh, it's supposed to be GL. That's not defined. We'll just comment that out. Alright, we got some syntax errors. Great. It says program not linked. Syntax error. Alright, let's see. I got a syntax error. How do I get a syntax error? Attribute vec for void main looks right. Void main, GL frag error. Copy. Vec41. Yep. I don't see half of syntax error. It says the error is a bracket. I don't understand. Oh, dot text, because that makes sense, because it's an object. I want the text of it. Now it's starting to make sense. Alright, so it says program not linked. So when I try to get the attribute location, so it looks like when you get the attribute location, it says program not linked. What the heck does that mean? So you create the program. Oh, I did it wrong. And then you call attach shader, and then you link the program. So we're just going to create a function called create program. And it's going to do all the linking. So const program. So you create the program. And then we're passing the GL. And we're going to do vertex shader. And then we're going to do the fragment shader. Yeah, and then we do GL attach shader. Attach. And then attach the fragment shader. And then we link the program. attach the verb to the program. Attach the fragment shader to the program. And then we will link the program with WebGL. And then we return the program. So create program, pass in GL, the vertex shader, and then the fragment shader. Oh my goodness, it worked. Oh gosh, I'm tired. Alright, so finally we created our first 2D object using WebGL. Oh wow. Wow. Let's actually change this to 1. Let's make it a little bit bigger. There we go. A left triangle. 2D graphics, it worked. Alrighty, and that did it. Well, I learned some things today. And that's it for today. I think I'm done. We'll have to come back to this another time. But for the most part, that all made sense. So for WebGL, you have to create 2 shaders. The vertex shaders for positions, and then fragment shaders for rastering. So we get the GL global object from the canvas, and then we get the text of our vertex shader and our fragment shader in GLSL, and then we create the shaders by simply calling create shader, passing in the type, whether it's vertex or fragment shader, and then passing in the code to our shader, and then compiling the data, and then returning the shader. And then we create our program by using both the vertex and the fragment shader, and we get our attribute location from that program. And then basically we need to pass in the data to our vertex shader. So what we do is we create a buffer, we pass in our buffer, we bind our buffer to a global variable in WebGL, and then we pass our data, we convert our data into float32, and then we pass that data into the global buffer, and then we enable the attribute, and then we tell the attribute how to get the data from our buffer, which we tell it to get 2 at a time in their floats. And then we tell our WebGL to use our program, and then we draw triangles for every 3 vertices that it finds. And the way we create our program is we basically call create program, we attach the vertex shader and the fragment shader, and then we link it to WebGL. I mean, that wasn't too bad. Yep, wasn't too bad. Alright, that was a lot for one day. I think I will call it wraps. We'll come back to this next time. Hey, what about to. I didn't even know what about to had followed. It didn't even do a message. What is going on with my stuff? Wait, let me see. Yep, it says what about to has followed. Thank you for following my stream. I don't know why my follow button, my alert box. Um oh, maybe I just didn't hear it. Maybe it says it's working. Yeah, I just didn't hear it, maybe. Yep. Well, thanks. What about two? Thanks for following. Thanks for following. I appreciate it. But yeah, I think that's a good stopping point right now. So I'm on the verge of greatness, I believe. Because I think I got the concepts pretty good for at least 2D. So, and I'm pretty much. Where did I leave off? I'm almost halfway done with this article. I think the only difference for maybe I think this is the main concepts though. So I should be able to breeze through some of this a lot easier. Like, what the heck is this? By the end of this, I should be able just to make a game. So that's the end goal here. Yeah. So we'll make our way through these tutorials and then orthographic 3D. Oh my goodness. That's the end goal here. Is to do 3D animations. Look at all this math, all this matrix transformation and stuff. See the 4x4 matrix multiplication just to do some 3D animation. Look at that. Like, that's ridiculous. Look at this. Oh gosh. But yeah. At least we got something today. We got a simple 2D triangle. And then hopefully I can get to this event stuff later on. And then we can make some games. Alright, so that is it for me today. I'm tired. Writing all this code was exhausting, so. And learning all the concepts just to create a simple triangle. There's also 3D libraries. There's three, it's like you don't have to do this. Like, this is just for learning purposes, but there's basically 3D libraries that do most of this stuff for you. But anyway, so that is it for me. Thanks for tuning in. I know this was kind of boring because it was like a lot of concepts that even I didn't know. But for the most part, I think I got it just enough. to get by, but we'll keep working at it. All right. Anybody have anything to say before I get off? Before I leave? All right. Well, I would like to give a special thanks to Dark Chris for coming to my stream. I appreciate it. Dark Chris is always showing up, so I very much appreciate it. I'm probably gonna stream Thursday. I think I want to stream a different game. I think I'm gonna purchase a game. Lost in Random. I think I'm gonna purchase that. I think that's on PC. If it's on PC, I'm gonna buy it. Let me see. Yeah, it's on Steam, so I'm gonna buy it on Steam, and that'll be my next stream. Lost in Random. And 29 bucks. It's good. With even and odd, it's only 20 gigabytes. So that's what we'll do. We'll stream Lost in Random. Wait, can I do it on Twitch? Let me make sure that I can stream this on Twitch before I try. Huh. Yep. People are playing Lost in Random, so that's cool. Alrighty, well, that's it. Alright guys, I am off. Thank you for watching. Thank you, Dark Chris. And thank you, what about two? For following. So alrighty, I will talk to you guys later. I will be streaming Thursday. Cue outro.